Spherical mirrors. Image formation by spherical mirrors. A highly polished surface, such as a mirror, reflects most of the light falling on it. As a result of reflection, images are formed. There are two types of mirrors, namely plane mirrors and spherical mirrors. All of us use mirrors in our daily life for personal grooming. These are plane mirrors. The reflecting surface of these mirrors is plane. The reflecting surface of a spherical mirror can be considered to form a part of the surface of a sphere. If the reflecting surface is curved inwards, that is, faces towards the center of the sphere, it is called a concave mirror. If the reflecting surface is curved outwards, it is called a convex mirror. A concave mirror converges light rays that fall on it, whereas a convex mirror disperses light rays that fall on it. Because of this phenomenon, these mirrors are used for many real-life applications. Concave mirrors are used in solar furnaces to concentrate light on a point. They're also used by dentists to see the enlarged images of teeth. Convex mirrors are used in rear-view mirrors of vehicles. They are also used as reflectors in street lamps so as to diverge light over a large area. Take a small doll and a plane mirror. Place the mirror in front of the doll. You are able to see two dolls now. Move the doll to and fro on the table. The image also moves accordingly. Now let us place a scale in front of the doll. Observe the image. The image of the doll will be formed after the image of the scale. That is, the distance between the object and the mirror and the distance between the image and the mirror will be the same. Now use the scale to see the heights of the object and the image. We come to the conclusion that the size of the image is the same as that of the object. From this demonstration, we have understood that in the case of a plane mirror, the image is located as far behind the mirror as the object is in front of the mirror. The image formed will be of the same size as that of the object. To understand image formation in concave mirrors, we use ray diagrams. Let us now see some of the conventions used in a ray diagram. In a concave mirror, the normal to the surface varies at each point, and all of these converge at the center of the sphere. This point is called center of curvature, represented as C. This is also the center of the sphere. The center of the reflecting surface of a concave mirror is a point called the pole. It lies on the surface of the mirror. The pole is usually represented by the letter P. Principal axis. An imaginary line passing through the center of curvature and the pole of a concave mirror is called the principal axis. Now let us consider a number of rays parallel to the principal axis falling on the concave mirror. Rays after reflection from the surface intersect at a point on the principal axis of the mirror. This point is called the principal focus. Take a concave mirror, a doll and a screen. Let us also draw the ray diagram side by side. In the ray diagram, draw the principal axis and identify the points P, pole, C, center of curvature, and F, principal focus. F will be exactly in between C and P. In the real experiment, identify C plane, F plane, and P plane. Let us keep the doll at different distances from the mirror and see how images get formed. Let us keep the doll very far from the mirror. The screen is in the same plane as principal focus. As you can see, a small image will be formed on the screen. Let us have a look at the ray diagram. When the object is very far or at infinity, the rays from the object will be parallel to the principal axis, and hence all of them will converge at F. Let us now bring the doll a little forward but little behind the C plane. Let us shift the screen between C and F planes. You can see an inverted, diminished image on the screen. For drawing the ray diagram, we need to consider 3 rays. 2 of these start at the top of the object. One travels parallel to the principal axis and gets reflected from the mirror. The other ray goes through the center of curvature. The size of the object depends on where these 2 rays meet. The third ray travels along the principal axis and gets reflected on the same line. Let us now keep both the doll and the screen at C plane. The image will be formed on the screen with the same size, but it will be inverted. The rays in the ray diagram traverse as shown. Let us now move the doll a little forward, now between C plane and F plane. The screen should be kept beyond C plane. Now you can see an enlarged image on the screen. Now move the doll to F plane. Move the screen far away from the mirror, out of frame. For the object at F, image is formed at infinity. Note that in all the above cases, you captured the image on the screen, which means the image is real. Now let us move the doll even closer to the image so that it lies between F plane and P plane. You can see an enlarged image inside the mirror. This is a virtual image and cannot be captured on the screen. Now let us have a summary of the position, nature and size of the images for various positions of the object in a concave mirror. Just observe the image position as the object is moved on the principal axis. From this demonstration, we've understood that in the case of a concave mirror, the position, size, and the nature of the image varies depending on the position of the object. Let us first identify the center of curvature C, pole P, and focal point F of a convex mirror. For a convex mirror, F and C falls behind the mirror. Let us take a doll and a convex mirror. Keep the doll at a large distance from the mirror. If the object is at infinity, then a point-size virtual image is formed at the principal focus of the mirror. Hope by now you understand what is meant by virtual image. It means that you cannot capture that image on the screen and it is formed behind the mirror. The light rays actually do not originate from the image but appear to originate from the image. The light rays actually get reflected. Now let us bring the doll a little forward, somewhere near the mirror. The rays coming from the doll will get dispersed in all directions, but appear to originate from a place behind the mirror. You can see a diminished virtual image on the mirror. Let us also understand the ray diagram for this scenario. The 2 rays starting from top of the object will not intersect at all, but they will appear to be intersecting at a point behind the mirror. From this demonstration, we have understood that in the case of a convex mirror, the position and the size of the image varies depending on the position of the object. The image formed by a convex mirror is virtual. You have now understood reflection phenomena of light, spherical mirrors, and their applications. You have also seen some of the real-life applications of spherical mirrors. Can you now list some other real-life applications of spherical mirrors?